Hi,
Hi, Louis. How are you?
doing well. How's it going?
Oh, it's going okay.
Good to see you.
Nice to see you too. How's it going with you?
Oh, it's going well. I started teaching in person a few weeks ago.
Oh my God,
It's
dangerous.
something to get used to.
Yeah.
So you know the legacy of this lockdown, Olga will not appreciate it, is that I bought for $40 a beard trimmer on Amazon. And let me tell you, it makes for a nice clean cut. I wasn't a suggestion, John. Yeah, but it is funny, all those years of going to a barber and then you buy this thing and zoop. Anyway. I'm gonna keep that part of this log of the whole experience. Okay, now we have.
I was actually doing pretty similar that my wife was giving me haircuts with a trimmer, but you know, it's been a while.
Yeah. No. You just, well, there's also the factor as you get older, you don't care anymore. When I was young, nobody was gonna cut my hair like that. Now it's just, anyway.
So John, you can try to share your screen and all that kind of stuff.
Great.
See if it works.
I unfortunately double booked. I've got a meeting in 15 minutes, which I'll cut out for and come back if there's time.
Can't you just walk your laptop down and listen to the talk in the meeting?
You can.
Supposed to pay attention to the meeting, you know.
Who was it? Somebody, we were doing Zoom and she had 2 Zoom meetings and 2 Zoom talks and a meeting at the same time. I think Olga was there. Who was that pulled that stuff? Natalie, one of the Italian people that had all these committees.
Should
What?
we really name this person?
Marie?
No, I'm saying, should we really name this person? Because
Oh,
maybe
yes, okay, you're gonna be modest. Yeah, no, anyway. The Zoom, this whole thing brought out the best talents of people. I mean, you physically cannot have 2 meetings at once if they're held in person. You could, but on Zoom, piece of cake. Actually, 2 laptops are needed, but
You can use your smartphone.
yeah, maybe that, was that? Okay, I can't say her name, but yeah, she had the smartphone and the laptop.
There have been times where I'm in a class and I need to hold office hours over Zoom. So no one usually came to the office hours. So I left class if that happened, but otherwise, if class was going over.
Hello, everybody. Hey, John.
Morning, Jeff.
Hello.
Good to see you.
See everyone.
Yeah. So. Wow. Well, yeah. So I guess happy beginning of fall to everybody. It finally feels like summer is over. And I guess we can get started. Are you ready, John? Are you?
Yeah, I'm ready.
Yeah, okay. So we're happy to have Jon Chaika talk about ergodic theory.
Okay, so this is the first of a 2-part talk, and this is sort of just to kind of motivate the second talk, which is going to be a talk about sort of a little bit about what the space of invariant measures for a particular dynamical system can look like. So I want to talk a little bit about kind of invariant measures today. I hope I've pitched this at the right level. I might not have, but I'm not sort of assuming any knowledge before this talk. So I have two things, which is one, no question is sort of no question is too basic, because I'm not sort of assuming anything. So if you don't understand something, that's my fault, not your fault. Please feel free to ask a question. And then the second thing is I'm very bad at monitoring chats when I'm sharing screens in this way. So if somebody either A, could monitor the chat and shout out to me if there's questions in it, or B, if somebody could, or feel free to shout out yourself questions you have, please do that. Okay. All right, so I'll get started. Thank you very much for the invitation to give this talk. And in particular for setting aside so much time to give me 2 opportunities to give a talk. I really appreciate that. I wish I could be seeing people in person in wonderful Austin, but this is the way the world works for now. So it's really great to have this opportunity to talk with people who are even beyond Austin. So that's great. Okay, so what is ergodic theory for the purposes of this talk? Ergodic theory is a sub-area of dynamical systems which wants to understand the long-term behavior of points as you apply a system, a map to a system, points as the system evolves, maybe it's given by time evolution, by using measures. That's sort of the ideology of the talk today. And maybe ergodic theory means different things to different people in different settings, but that's what I think it is today. Okay, so what's the setting for this talk? So the setting for this talk is we'll have a compact sigma compact metric space. In fact, it'll often be compact. We'll also have a map from the space to itself, which will be always continuous, and oftentimes it'll be a homeomorphism. Okay. And then we'll have a measure that's preserved by the dynamics. So if you take if you take everything you see and you move it forward by 1 step of the dynamics, the measure sees the same world. So that's a probability measure, so that if you look at the pre-image of any measurable set, the measure that you assign to that is the same as the measure of the original measurable set. Right? So that's going to be sort of the setting of today's talk. And there should really be a sigma algebra. It can be the Borel sigma algebra or the completion of that with respect to mu, but that will be suppressed for the entirety of the talk. And given the nice topological setting I'm working in, there's sort of no issues with that. But please feel free to ask questions if anything comes up with that. Okay, is everybody happy about this?
Can you remind me what sigma compact is?
A metric space is sigma compact if you can write it as a countable union of compact subsets of itself. So for example, the real line is sigma compact because it's exhausted by the compact closed intervals from -n to n, and then you union as n goes from 1 to infinity. Thank you for that question, Hunter. Any other questions? Great. So let's give a name for this. We call this a probability measure preserving system, okay? Because it's a system that preserves a probability measure. All right, so let's do one example of this. So a nice example is given by a rotation of the circle, a rigid rotation of the circle. So I start out with the unit circle in the complex plane. So every point there has a representation as e to the 2 pi I x, where x is a number between 0 and 1. And then I want to move by moving an alpha's proportion of the circumference. So my point e to the 2 pi I x goes to e to the 2 pi I x plus alpha. Okay, that's a nice map. So I move by a arc of size alpha over, and I get this. Now I move by my next arc of size alpha over, and I get the next point, and you can sort of keep repeating it over and over again. Okay, so this is clearly a map of a sigma compact metric space, in fact, a compact one to itself. It's clearly continuous. And moreover, it preserves Haar measure. Indeed, this map is just given by multiplication by e to the 2 pi I alpha, right? This is just composition by a group element. And so it preserves the Haar measure. Alternately, you might want to think of Lebesgue measure sitting on this sort of one-dimensional object, in which case this is an isometry, and that preserves the Lebesgue measure. So either way you look at it, it sort of preserves this measure. Is everyone happy about this? Great. Okay, so now we come to the next important definition of this talk. We have a couple more definitions, but this is the definition of ergodic. And ergodic is a notion of indecomposability of our system. So if we have a probability measure preserving system, we call it ergodic if any set that's almost not sent off of itself. So we look at the pre-image of the set and we subtract the set from it, and we ask whether or not that's negligible. Okay. If that is negligible, then this set either has to be nothing from the standpoint of measure theory, so it has measure 0, or it has to be everything from the standpoint of measure theory, so it has to have full measure, which is, in this case, that its measure is 1, or more generally, that the measure of its complement would be 0. Okay, so this is a notion of indecomposability. It means your probability measure preserving system doesn't break into 2 subsystems, which remain invariant as kind of measurable objects. All right. So this definition has a great consequence, which is called the Birkhoff ergodic theorem. So if your measure is ergodic and you have an L1 function with respect to your measure, then for almost every point, as you start moving forward by the dynamics and you evaluate your function along this orbit as you're moving forward by the dynamics, and you take the average of that, you converge to the integral of your function over the whole space. So you kind of, if you think about your map as being kind of an evolution of time on your system, you start out with just an individual point in your system, and you start marching around your system over time. And you just observe, every time you land, you make an observation. And as you average this over time, you recover what you would have gotten if you observed everywhere and averaged over the entire space. So the jargon of this is that the time averages are equal to the space averages. The left-hand side is the time averages, and the right-hand side is the space averages. And you ask this maybe not to hold for every single point, but you ask this to hold for a typical point with respect to your measure. Is everybody happy about this? Great. So let's make some quick remarks. So one thing is the quantifiers on this are a little funky. We pick our observable, and then we get a full measure set. You could ask whether you might have better quantifiers. And in fact, there exists a full measure set. Let's call this G sub mu. So that for all continuous compactly supported functions, the summation of f of t to the I of x and minus 1 over n converges to the integral of f d. So if we restrict ourselves to continuous compactly supported functions, we can get one full measure set, which works simultaneously for all of these functions. And this isn't particularly hard. So what are the observations? The first observations is that in this setting, there's a countable subset of the continuous compactly supported functions, which is sup norm dense in the continuous compactly supported functions. And then the next observation is that this property behaves nicely with respect to closures in the sup norm. So if it holds for a family of functions, it also holds for the sup norm closure of that family of functions with respect to the point x. Is everybody happy about that? And that's just because both sides don't change very much. And this is different than L1. This does not play nicely with L1 closures because the right-hand side plays nicely with L1 closures, but there's no reason for the left-hand side to play nicely with L1 closures. Okay. All right. And there's a version of this that holds for if you just restrict to invariant measures rather than these kind of extreme ergodic ones. There's a version of this too, where almost every point with respect to your invariant measure will converge to an integral with respect to some ergodic measure, where that ergodic measure is allowed to depend on the point. So this funky ergodic measure depends on X. And maybe I should just make one thing to be explicitly clear. Ergodicity is clearly a necessary condition for the Birkhoff ergodic theorem. Because imagine you had that you were not ergodic. So that means that this fails and there exists some invariant set A of positive intermediate measure. Then the characteristic function of A won't satisfy the conclusion of the Birkhoff ergodic theorem as stated here. So the Birkhoff ergodic theorem states that the obvious necessary condition is actually a sufficient condition. So yeah, everybody happy about that? Great. Okay, maybe I should just make one more remark that a proof of the ergodic theorem would probably take most of a lecture like today, but I have a favorite reference for it, which is a paper in the Israel Journal by Katznelson and Weiss. That's my favorite proof of the Birkhoff ergodic theorem, if anybody is interested in reading a proof and hasn't seen it. Okay, all right, so what we've had, so this should motivate that sort of invariant measures and maybe slight strengthenings of them, ergodic measures, are a good way of probing the behavior of points over time. This was the ideology I set up originally. And the Birkhoff ergodic theorem suggests this. But then another question we can ask is, can you ever run this strategy, right? If you have ergodic measures and you have invariant measures, maybe you can run this strategy. If you have invariant measures, the Birkhoff ergodic theorem gives you some nice conclusions. Now, maybe you never have invariant measures, right? Maybe you can never get this strategy off the ground. And the Krylov-Bogoliobov theorem tells you, fortunately, you can. Okay, so here, if you have a compact metric space and you have a continuous map of that space to itself, then there exists some invariant measure for your system. Okay, so that's saying that sort of the assumptions, at least of the second part of the Birkhoff ergodic theorem, you'll be able to run it, at least if you assume your space is compact. Now, as Hunter asked in the beginning about sigma compactness, why am I not saying sigma compact here? Because it's not necessarily true for sigma compact spaces. For example, if you think of the integers, that's a great sigma compact metric space. And you just think of +1 as a map from the integers to itself. It's a great homeomorphism of this sigma compact metric space, but it doesn't have any invariant probability measures. Okay? It has an infinite invariant measure, counting measure. It also has sort of the zero measure, which is sort of an invariant finite measure, but it doesn't have any invariant probability measures. Okay, so compactness is sort of a natural assumption here. Okay, so let's prove the Krylov-Bogoliobov theorem. I love this theorem and I get to prove it, so I'm super excited about that. So the proof is basically quoting another big theorem and making a definition. So the other big theorem I want to use is Banach-Alu-Agalu, which is about weak star compactness. And then the other thing is I want to make a definition. So this notation here, this is point mass placed at t to the I of x. So this is the measure that for a measurable set gives it size 1 if t to the I of x is in it, and otherwise that measurable set has size 0. So this is a perfectly good Borel probability measure. Now what I do is I take an average of these measures along a long orbit segment of length n, and I take the average of that. Everyone happy about that? Okay. Now, any weak star limit of this is going to be t invariant. So this isn't all that hard to show. You can show that So the easiest, so let's just kind of very quickly outline why that is. T of nu of x comma n minus nu of x comma n is a very small measure. What is it equal to? It's just going to be equal to, I'm going to put a point mass at t to the n of x. And from that, I'm also going to subtract the point mass at, just at x. And this is just because of telescoping sums, right? This is just an immediate consequence of telescoping sums. And then the other part is because t is continuous, t of the limiting measure is limit of t of the measures. Okay, so this uses the continuity of t. So the first thing I did is sort of true in general. That doesn't, there's nothing about the continuity of t here, but the fact that we can probe the limit by applying t to the prelimits, that's using the continuity of t. Everybody okay with that? Great. Okay, and now we just need that we have a limit. Now we just need that we have a limit. And the set of Worrell probability measures on a compact metric space endowed with the weak star topology is itself a compact metric space. And in particular, what this means is every sequence has a convergent subsequence. So here was just a sequence where I knew that any limit of it had to be t invariant. And then I know that there has to be a limit. And so let's refer to this previous example I talked about with the integers. So this definition works perfectly well for the integers, right? It's just going to be the average of point mass on longer and longer segments. Say I started at the point 0, it's going to be like the average of delta mass at 0 out to n minus 1. Perfectly good measure. But that's going to converge in the weak star topology to the 0 measure. And this is a phenomenon called loss of mass. All right. Any questions on the Krylov-Bogoliobov theorem? Great. So now this theorem motivates to me a pair of definitions. So we can ask what measures arise from this construction. And we call a measure that arises from this construction a quasi-generic measure. And we call a point to be quasi-generic for the measure if the point gives this measure as part of this construction. So what you're doing is you're looking at these measures where you're putting point masses along orbits, and then you're wondering whether there's some subsequence of these measures that converges in the weak star topology from you. And if so, you call this point quasi-generic for the measure. If the measure has such a point, it's called a quasi-generic measure, and so forth. And you can also ask if there is, what if you have actual convergence, right? That's a natural thing in in sort of general. You might have convergence along subsequences, but maybe you want actual convergence. And when you want actual convergence, you call that generic. Okay. Everybody happy with that?
So just to clarify, the kind of the reasoning for the word generic is that we're kind of thinking of X is like a generic point, like if you were to sample from mu.
Exactly. Yeah, so yeah, let's say, thank you very much for that question, Hunter. So let's go back a little bit to the Birkhoff ergodic theorem. So this consequence of the Birkhoff ergodic theorem, that for continuous compactly supported functions, there's a full measure set where you converge to. All of these will be generic points. Maybe I should use a different color. These are all generic points from you. Okay, so the typical point for mu, if mu is ergodic, is going to be a generic point in this sense. And they have sort of an explicit condition, which lets you then, you're talking about a sort of explicit full measure set. And moreover, it's sort of a natural set from the standpoint of dynamics, because these probe the space according to your measure, at least from the standpoint of topologically nice functions, continuous compactly supported ones. Did that answer your question, Hunter?
Yeah, totally.
And thanks for the question. It was a great question. Very helpful. Okay, so that's genericity and quasi-genericity. Okay, maybe, so I had some space here where I would talk about the structure of the set of invariant measures. Are people familiar with the fact that invariant measures for a dynamical system are convex sets, and that the ergodic measures are extreme points of them? Great, then I'll move on, I guess. Does anyone want me to explain that, or I'll just move on otherwise? Great, I'll move on. I hope I paused long enough. So I want to talk about a good news result and a bad news result. And maybe causing
John,
yeah.
can I ask about that actually? What is this statement? So I see why they're convex, but you're saying every extreme point is ergodic, or the ergodic ergodic measures are extreme, but there could be other extreme points. What is the situation?
Yes, the extreme points are exactly the ergodic measures.
Ah, okay.
I'll just quickly say why this is.
Okay.
There's some words you could say. So first, assume that you have a measure that's not ergodic. Then you have two invariant sets. Your measure restricted to those invariant sets is going to be an invariant measure. You renormalize, so it's a probability measure. You write your original thing as a weighted combination of those. Your non-ergodic measure can't be extreme.
Yeah.
On the other hand, so that's saying not ergodic means not extreme. So now I want to say that not extreme is not ergodic. So now I have a point that's somewhere in between two different measures.
Yeah.
I can look at the Radon-Nikodym derivative of both of those measures with respect to that original measure. And those are going to be T-invariant functions. And you can, and they're going to be constant almost everywhere. So you can look at those sets, and that will give you sets that will certify that this measure is not ergodic.
Okay, thanks.
No problem. Okay. So now if we have a compact metric space, and mu is the only preserved, and a continuous map on it, and mu is the only preserved measure, then every point is generic for this measure. So this is sort of the dream situation that I set up at the very beginning of the talk. I want to understand the long-term behavior of points, and I want to do it using measures. So here I look at a system where I have some basic topological assumptions on it, and the only additional thing I know is I know its set of invariant measures. And then I gain a complete understanding, in some sense, of the long-term behavior of every single point. Is everyone happy that that's sort of what this theorem is saying? And this theorem has a super easy proof. If this is not true, the proof of the Krylov-Bogoliobov theorem would produce a different invariant measure. So let's assume there's a point that's not generic for my measure. So that means that there's a point so that this sequence of measures does not actually converge in the weak star topology for mu. So that means there's a subsequence where it stays away from mu. And because of compactness, once again, there's a further subsequence where it converges to something else. But this first step always produced a T-invariant measure. So we would have gotten a different T-invariant measure. Everybody happy about that? Great. And then the next one, which kind of you could think of as being the bad news, maybe that's the wrong way of thinking about it, which says that if you have a compact metric space, and it has the additional property that the orbit of every point is dense, then there exists a point which is quasi-generic for every ergodic measure. So in particular, if you have more than one ergodic measure, its long-term behavior doesn't coalesce on one thing. It oscillates between at least two different behaviors. Okay, so maybe you could think of this as being bad news because the understanding we're getting of the orbit of every point isn't going to be as good. But maybe it's good news because it sort of tells you the limit of what you can sort of hope for. Can't say every point has a limit, limiting behavior. Everyone okay with that? I guess I can do one of two things. I can give the proof of this, or I could move into examples. Do people want to see the proof of this?
I'm thinking for the second theorem, but this is sort of like ergodic decomposition.
So
But-
so to me, the proof is basic. Yeah, let me prove it. Okay, so it's a consequence of the bare category theorem. So the bare category theorem is one of my favorite theorems. I love it. It says that if you have a complete metric space and you have a sequence of open and dense sets, their intersection is non-empty, and moreover, it's dense. So the conclusion of the bare category theorem is about these countable intersections of open sets. And so this motivates us to make a definition, which is a G delta set is a set that can be written as a countable intersection of open sets. And by sort of running the proof of the bare category, so by running the bare category theorem again and rewriting your sets, a corollary of the bare category theorem is that a countable intersection of dense G delta sets in my complete metric space is itself also a dense G delta set, right? You write each of these as a countable intersection of open dense sets. And then that countable intersection of countable intersections is also a countable intersection. And so the bare category theorem gives you it's going to be a dense set. It's clearly a G delta. So this motivates that G deltas in complete metric spaces are a good notion of big sets. They're so big, in fact, that if you take a countable number of them, you're still big. Okay, so now I want to complete the proof of this so-called bad news theorem. And so we have a proposition, which is that if mu is an ergodic measure for t, then the set of quasi-generic points for mu is a G delta set. Okay, and so this, as often when you're sort of proving results like this, you want to sort of come up with the right definition. And so the right definition to look at is the set of x's, so that when you look at 1 over n, summation from I equals 0 to n minus 1 of f of t to the minus I of x minus the integral of f is less than epsilon for all one Lipschitz functions. So this is a set, it depends on epsilon and n. I want to look at the interior of the set, and I want to take the union. So this is sort of the key set to look at. This is the key sort of open condition. And then you want to take the union over the n's, and you now want to take the intersection of x epsilon equals 1 over n from n equals 1 to infinity. And this is a way of writing it as a G delta set. Okay. Now let's notice that this is only asking that for each epsilon, there exists some n. So this is a quasi-generic type condition. It's not a generic type condition. The intersection gives you subsequences. It doesn't give you sequences. Okay. All right. And then so the next observation is under our assumptions that the orbit of every point is dense, every invariant measure is fully supported. Every ergodic measure is fully supported. Okay, and that's because the orbit of every point is dense and our nice compactness assumptions. Okay. So what we have is for each ergodic measure, we have an open, we have a G delta set that contains a full measure set. So it's going to be a dense G delta set. That's sort of where the denseness comes from. Now you could ask, what if we have an uncountable number of ergodic measures? Well, we have a countable dense set of ergodic measures, and it's enough to be quasi-generic for all of those measures. And then you'll be quasi-generic for the closure by choosing a diagonal subsequence. Okay, and that's the proof. So did people follow this proof? Or should I go to any of the details?
I feel good.
Great. All right, so let's do some examples. So the first example I'll do is a case of the nice theorem, where we gain a complete understanding of every point. So let's look at rotation of the circle, this nice system I started with, and let's assume that this alpha is not going to be a rational number. Okay, it's not going to be rational. Then for every point, what I want to do, what I claim is that this is going to, the orbit is going to weak star converge to Lebesgue. Okay, so let's try and go through the proof. So I want to first test on nice functions. So I test on functions of the form e to the 2 pi I kx. X goes to e to the 2 pi I kx. In our setting, this is the same as the function z goes to z to the k on the unit circle in the complex plane. Okay, and I want to just start out the point 0. So I consider these sort of long-term averages as for a given function. Right, the weak star topology is all about probing what's happening for continuous functions. So I just want to probe what's happening for this one function. Okay. Now this is a geometric series, because and so this is going to be its limit. Okay. Now, since alpha is not in Q, if k does not equal 0, then the denominator is greater than 0. The denominator does not equal 0. And it's constant in capital N. Now the numerator is bounded at most by 2. And you're dividing this whole thing then that's bounded by at most 2 over a constant by n. So this goes to 0. Okay. And it goes, so that's sort of a nice result. And moreover, what we have is this is going to go to 0 for all. So what happens to this for trigonometric polynomials? So for trigonometric polynomials, so if f is a trigonometric polynomial, that means a linear combination of functions like this by e to the 2 pi I k z's, then the summation of f of t to r to the I of x I equals 0 to n minus 1 over n converges to the integral of f d Lebesgue, d har. And why is that? That's just going to be the coefficient. The integral of f d har is just going to be the coefficient of the constant term in the trigonometric polynomial. Okay? And that's the only term that doesn't die out, right? This telescoping argument doesn't work when k equals 0, because that's going to be, the denominator is going to be infinity, to be 0 in that case. So sort of the argument doesn't work. And so, yeah. Okay, is everyone happy about that? Now, because trigonometric polynomials are dense in the continuous functions, we have that you actually converge to your integral with respect to Lebesgue for all continuous functions. So my point e to the 2 pi I 0 is going to be generic for Haar measure on the circle. Right? Now, if I look at another point, so let's say I have a point P in the circle. Well, everything in sight changes equivariantly by multiplication by P. So what you have is you have that this point is going to be generic for an appropriate rotate of Haar measure, the rotate of Haar measure by P. Okay? Now, of course, that's Haar measure. because our measure is rotation invariant. Okay, so that's that nice case. All right, so I want to now say sort of a bad news. So another system where you sort of have crazy behavior is the one-sided shift. So let's look at my space X, which will be a discrete set, let's say a 2-point discrete set raised to the natural numbers with the product topology coming from the discrete topology on this 2-point set. So by Tikhonov's theorem, this is a lovely compact metric space. In fact, there's lots of nice metrics you can put on it. For example, this is a space of sequences in 0 and 1. And so you can look at two sequences and you can look at the first place where they vary. And the distance between those 2 points will be 1 over that place. Okay, that's a perfectly good metric that turns this into a compact metric space, gives it the product topology. And then I wanted to use a natural map, which is just shifting everything over to the left. And this has many ergodic measures. So it has periodic measures like the constant sequence 0. That's going to support an ergodic measure. Indeed, you apply the left shift to it, you get back the constant sequence 0, everything stays put. You could also look at the sequence 0, 1, 0, 1, 0, 1, 0, 1, and so forth. You shift that and you get the sequence 1, 0, 1, 0, 1, 0. And so if you shift that, you get back to where you started, 0, 1, 0, 1, 0, 1. So if you take the barycenter of those 2 points, that also is an ergodic measure where the dynamics of the left shift are 2 periodic. You just move between these 2 points back and forth. Everyone happy about that? Okay. So it has, and it's not very hard. You just fix any finite sequence you want, and then you just repeat that over and over again. That's another perfectly good, that will generate a perfectly good periodic ergodic measure. But there's other ergodic measures, for example, product measures. So I can define a weight to the symbol 0, and I can define a weight to the symbol 1. Because I want a probability measure, I want those 2 numbers to add up to 1. And then I can just take the product measure of that. And that's going to remain invariant under the left shift, because this probability measure only cares about what the symbol is. It doesn't care about where it's placed. So when I shift to the left, it doesn't see anything changing. Everyone okay with that? And there's a ton more that I don't really have time to explain. So I'll just suggest this by one example. So there's a particular sequence, you can call it the Touy-Morse sequence, and you can look at its orbit under the left shift and take its orbit closure. That's going to be an L invariant compact metric subspace of this space X. And it turns out that it supports a unique L invariant measure on it. That's going to be another ergodic measure on this space. And there's just a ton of these. Okay, okay, so in our previous example, the set of invariant measures were just 1 point. Here, you really have a crazy set of invariant measures. In fact, the extreme points are uncountable. Just the product measures alone give you an uncountable family of extreme points. Is everyone okay with that? And you can ask what the set of generic measures are. So what are the possible behaviors of points? Well, every single invariant measure has a generic point, not just the ergodic ones, they all do. And then things are even crazier. There's a dense set of points which are quasi-generic for every single invariant measure. So there are points where you can't really say much about their behavior. The obvious obstruction is the only obstruction. So by the proof of the Krylov-Bogoliobov theorem, any asymptotic behavior along a subsequence of any point will be an invariant measure. So the set of things you can be quasi-generic for is contained in the invariant measures. On the other hand, this is telling you that there's no better restriction, at least in this setting. So I don't know, I view this as sort of bad news, because you sort of can't gain any more information than the obvious restrictions. Everybody okay with this? Have people seen this before? Does anybody want me to say a little bit about why this is true?
I'm okay.
Okay, then great, I'll move on. So I want to talk about one more situation, which is sort of an intermediate situation. So what was the situation? In our first example, the set of invariant measures was very small. It was as small as it could be. It was just 1 point. And then we gained sort of a very good understanding of the behavior of every single point's long-term behavior in that orbit. The second situation, the set of invariant measures was very, very big. In fact, it's a so-called Paulson simplex, and the set of ergodic measures is dense in the invariant measures. And our control on the behavior of points was sort of not so great. Points could kind of go wherever the obvious obstructions let them go. And now I want to do an intermediate example, which it turns out that there is sort of a reasonably big set of invariant measures, and yet we still gain quite a good understanding of what happens to every point. Okay? So now we have the next setting, which is SL2R mod SL2Z, and mu is Haar measure on this space. And we can look at the flow. So this is no longer a group. SL2Z is not a normal subgroup of SL2R. So this is no longer a group, but still the group SL2R can act on the left, from the left on it, right? Multiplication of 1, 2, T01 makes sense on the left. It doesn't make sense on the right anymore. Is everyone okay with that? And I could just look at this map with respect to the push down, with respect to the Haar measure on this set X. And so points in X can be represented as so-called flat tori. So this is the space of lattices in R2. And so you can just pick 2 basis vectors for the lattices. And from that way, or I'm sorry, co-volume 1 lattices in R2. And so you can look at a basis for that lattice, and that gives you a representation of a flat torus. So I've done one here, where one of your basis vectors is this side, and one is this side, and you identify the 2 sides. So you identify red with red, and you identify the black side with the black side. Perfectly good space. Okay, so now 1T01 just acts on this picture. So what does it do? It takes this vector and you apply 1T01 to it. So if you kind of think of this as being the origin, you would just, this would be fixed, and then this point would move over by T times the height. This is H. Everybody okay with that? Great. And so I've done a little bit of cartoon of that. So that's if when it's 0.25, I move over by this. So I'm just applying 1.2501 to this picture. And I do the next thing to the next point. It moves over more and so forth. So this is the dynamics on this space. So it turns out, and this is, I guess, maybe Furstenberg, that no, it's Donnie probably, that mu is ergodic with respect to this flow. Okay? But there are other ergodic measures, and these are supported on FT periodic orbits. So if I look at a situation where I have a horizontal side, so maybe I start out with a rectangle. A flat torus that's a rectangle with opposite sides identified. Okay. So we'll call this H, we'll call this L, and F. So this is going to be the point X, and X to the F of L over H equals X. So what happens is when you shear yourself all the way over, so let me try and draw a schematic picture here. Okay. This vector here is the same as this vector here. It was in my original lattice. So it's just a different choice of basis for my lattice. So I've returned to my same lattice in R2. So I'm the same point in SL2R mod SL2Z. Is everybody okay with that? Great. Okay, so in these orbits, there's a one parameter family of these orbits, and they're parametrized by the period of the orbit, right? So as I change H and L, keeping H times L being equal to 1 to keeping my area 1 condition, I obtain a one parameter family of periodic orbits of longer and longer or shorter and shorter period, depending on how I'm varying them. Everybody okay with that? Great. Okay. As the periods get longer and longer, it turns out that these measures converge to mu. And I guess the right attributions of this are Sarnak, and using ideas maybe in Margulis's thesis. Okay. Sarnak did quantitative version of this, so he did more than just that. But if you just cared about that, probably the ideas are already in Margulis's thesis. And as the periods get shorter, these measures converge to 0. Okay, this is the escape of math phenomenon. So this space SL2R mod SL2Z is not compact, it's sigma compact. And in particular, if you look at having a basis vector for your lattice, having shorter and shorter lengths, this is going to leave every compact set. And its limit, if it existed, would be a lattice with a basis vector that was 0. That's clearly not a lattice. So that's a way you sort of leave the space. So that's as a sigma compact space that's not compact. And as your periods get shorter and shorter, you're containing lattices with periods that are shorter and shorter, and you're leaving every single compact set. Okay. So as periods get shorter, these measures converge to 0. All right, so what's our setting now? We have a space of invariant measures with an uncountable number of different extreme points, and they come in sort of 2 flavors at least. So one flavor is the Haar measure, and then the other flavor is a one parameter family of periodic guys that in one direction is converging to Haar measure, and then the other direction in the space of invariant measures is converging to the 0 measure, and in the space of probability measures, it's leaving every compact set. Everyone okay with this? Great. All right. So still the situation, kind of remarkably, even though there's a sort of a ton of invariant measures, we have a complete description of the dynamics of all points from the standpoint we have. So it's a theorem of Dani that every point that's not FT periodic is generic for mu. Right? So we have some points that are on periodic orbits. There's no way they're generic for mu because they're generic for whatever the periodic measure is, because they just run along that over and over and over again. Is everyone happy about that? Great. So you can think of, from the standpoint of these points, the dynamics are taking place on a circle, and you just move along that circle and end up back where you started. Now the circle is in a bigger space, but for these points, all they see is the circle. Does that make sense to people? That's the periodic orbit. And if you're not in that set, then you're automatically generic for this big measure mu. Okay, so a corollary of this is every point is generic for some ergodic measure. So to my mind, this is very good news, because we know that every ergodic measure has points that are generic for it. And this is telling you that now gives you complete understanding. Every ergodic measure has generic points, and every point is generic for some ergodic measures. And moreover, you're generic for the periodic ones, if and only if you're periodic, and otherwise you're generic for the big guy, the Haar measure. Okay? All right, so I should mention that this is sort of a very general phenomenon, and that happens in so-called homogeneous dynamics. And if you look at so-called unipotent actions let's say you have a 1 parameter unipotent flow happening on a Lie group mod a lattice, then what you get is you have that every point is going to be generic for some ergodic measure. And moreover, this point is going to be contained in the support of that ergodic measure. Okay, so there's sort of a big setting where this sort of remarkable situation happens, where even though you might have tons of invariant measures, sort of a big simplex of invariant measures, you gain complete understanding of sort of the long-term behavior of every point. Okay, thank you.
Okay, so let's thank Jon. I mean, is that the end of your talk?
Yeah, I think that's a good place to end.
Okay, well, let's thank Jon. Wasn't clear to me. Okay.
Oh, sorry.
I was like, yeah, so I'll just open it up for questions. You know, anybody have a question, just unmute your mic and ask.
I feel like there was this point where we had two ergodic measures. I think we were looking at the left shift, and you had two ergodic measures, and you took the barycenter of them and got another ergodic measure. Is that what happened there?
Oh, I hope I didn't do that, because I'm not allowed to do that. But I think maybe I can say something. So I did talk about an example of a 2 periodic orbit, which was given by 0, 1, 0, 1, 0, 1, so forth, and 1, 0, 1, 0, 1, 0. So the point mass at either of these 2 points won't be invariant because they're exchanged under the left shift.
Oh, okay.
And the barycenter of that will be an invariant measure. And it's actually an ergodic measure. And this is a general construction, right? You have a periodic orbit. The delta mass at each of the individual points isn't going to be invariant, but there's an easy fix. You just average over the one walk around the period, and then you get yourself a nice invariant measure.
Okay, yeah. Okay, I was confused. I was like, okay, we took 2 ergodic measures and took the barycenter. We got another one. How are these extreme points? Okay,
I hope I didn't say that, and I apologize if I did.
Yeah, I think I replaced some words in my head, so it's all good. I guess I have one more question. It seems like, so I guess it's more of a